Hello everyone, welcome to the course Mathematical Aspects of Biomedical Electronic System Design. I'm Ratin Joshi, TA of the course. I'm a PhD student at Department of Electronic System Engineering, Indian Institute of Science. In the previous TA class, what we saw is what are the different kinds of signals, what are the different types of systems. Also, we have seen a demonstration on moving average a system, how it smoothens and remove the high frequency burst and some of the unwanted noise in biomedical signals. In response to that video, I have received multiple queries regarding showing how I have generated the sinusoid functions, how I have added noises, which I have already shown there. But many of you have asked how I have generated the sinusoidal function. So it's a very basic thing. I believed at that time that most of you are aware. But anyways, we are going to see this in today's lecture. We will start from a scratch how to generate a signal, how to generate a sinusoidal signal, how to fabricate or how to get a signal which is near to what a physiological or biomedical signals uh, in order to understand the further processing of that. So we will see that in this lecture. We'll also see how Fourier transform is useful in biomedical signal processing. We'll see how it is being calculated, how Fourier transform is calculated as per the definition. We'll also see how FFT is calculated, why it is called a fast Fourier transform, and which is more feasible, or why FFTs are more frequently used. Also, we'll map it with the corresponding time domain waveform and see by changing a time domain waveform how it is reflecting in frequency spectrum. All this thing we'll see in this TA class. So let's get started. I'll try to add as much demonstration as possible, so it will make things easier for you people to understand some of this fundamental concept. One more important thing is, if you are working on any biomedical signal processing project, if you want me to cover some of the key concepts, or if you want me to demonstrate some of the concepts, feel free to write to me to my email ID or in the forum. We will try to include that topic in the course, which might help you in with your project or for your better learning. We'll start the demonstration using MATLAB. So yeah, this is a live editor in which I can code and type the text, which might be useful for your understanding. So I have chosen for this, instead of only demonstration, let's quickly generate a sine wave, or I should say sinusoidal wave generation. Okay, so what are the steps? I'll just list down the key steps. First, we'll define a time vector. We'll write an equation for sine wave, whichever frequency and all you want, and observe the time period, because this is mostly the case. Most of you are not aware that how can I generate a particular sine wave with a desired frequency. Plot and observe. Okay, so these are the basic things and the basic steps which you are going to follow. Okay, now let's realize this. In order to realize this, we'll convert this into a code. As discussed, we'll first define the time vector t. Now let me define in such a way that it would be from 0 to, let's say I want it till 10 seconds, but I want it at every millisecond. So this is my resolution. I need increment of 0.001 second, that is 1 millisecond, and I want it for 10 seconds. Okay, so this is how my time vector is defined. Now what I want to get, I want to just calculate the sine wave. I don't know what is value and all, but I just want to get the sine wave. I'm more interested in getting the relationship between the frequency of this wave and how I can change it. need a controllability on the frequency, which most of you have asked, and then I can simply plot it with respect to y. Okay, so let's quickly run this so you will get an idea how it will look like. Then we'll play with this and we'll identify how frequency can be obtained and all. So yeah, you can see that we have defined time from 0 to 10, it is here, and sine wave, so it starts with 0. How we can identify the time period of this? So we know that for sine wave behavior, it will repeat like this. Suppose the good thing about live editor is, see, I just have to increase here 20. If I run the same thing, okay, I'll get corresponding result quite easily. So in order to give you an idea what is the time period, this is getting repeated, right, 3 times almost in 20 seconds. So we can say that 20 by 3, which is around 6 point something, would be the one time period or something. But how to get it precisely? We can get the data tips from here. When exactly it is equal to 0, somewhere here. Let me just try. Somewhere here, yeah. So around 6.3. Okay, around 6.3 it is 0. If I can little drag it, yeah, to get the more precise, yeah, if you can see 6.29. So all this thing, we all know that sine waves time period is 2 pi. So 2 into 3.14 blah blah, it comes around this. But we have written an expression as y equal to sine t, just given a period of 6.28. Some of you wants it in more better order, or you want to keep the sine frequency as sine waves frequency as 2. How to get that? So there is a format. Okay, for sine t, I'll just write it here for your better understanding. Text, we'll switch to text. For sine of t corresponds to a period of 2 pi, which is nothing but 6.28, something like this. Okay, whereas you need a period of how much? Let's say I need a period of 4. Okay, then what should be the expression, okay, or equation which we have written? Now you see the period of 2 pi is obtained by writing a t here. Okay, now if you want the same thing to get repeated after 4 seconds, okay, so for that there is a formula, or there is a structure, sine 2 pi. What if it was sine of 2 pi t? Okay, 2 pi t instead of t, what if it is sine of 2 pi? 2 pi we are already writing. So in a way, what we are doing, we are scaling this entire scale. Instead of t, now we are multiplying with 2 pi. So for in between 0 to 1 only, you will get the one time period. Again, I'll repeat, y is equal to sine of t. It has a period 2 pi. Okay, now what I am doing is I am changing the signal. Y2 is equal to sine of t. I am keeping as it is, just multiplying it by 2 pi. What it does is it will multiply your x-axis, which was moving here from 0 to 2 pi for one iteration. Now it has a multiple of 2 pi. So instead of 0 to 2 pi, it will get all the value in between 0 and 1. Little difficult to understand, but once you understand, you can clearly have an idea that why this period is now not 2 pi but 1. Okay, in other words, the format for sinusoidal wave generation, which most of you know, we write it without completely understanding that why it is like this. Suppose let's name the signal as Z. I'll keep the time vector as it is, but the formation is like 2 by some number. Okay, I'll just put here f into your time vector. What you are doing is you are multiplying it, you are multiplying your time axis, which was earlier just a time variable, with by 2 pi in order to get integer frequency. in order to get a integer time period. Okay, so let's quickly realize this again in terms of code. So what I will do is I want to plot it here only, it will be better. So first I will hold this graph, that I don't want to plot it in another separate graph, and I will plot it as z is equal to sine of 2 into pi into. Now as we mentioned, we want a period of 4. Okay, now period of 4 means in 20 seconds, if I say period of 4, it will get repeated 5 times. Okay, so a period, I can write here, period is 4 seconds. Okay, which implies that it repeats after every 4 seconds, right? And which means it has a frequency of 1/4 hertz, which is nothing but 0.25 hertz. So your frequency, or how rapidly you want this sine wave to repeat, is 0.25 hertz. So I'll just write this 0.25 hertz here as it is, and I will put this 0.25 hertz here, which is nothing but your f. So, and your time vector will remain as it is. Okay, here what you are saying is I want this particular waveform to get repeated in how much period of time? 4 seconds. And let's quickly see that whether the same holds or not. So let me run this section. Okay, so you will get an idea that how it is getting repeated and how you are getting a value though. I have to plot it as well. So t comma z, these are the values. If I plot it, should be 0. Yeah, auto suggestions are. Yeah, now if I plot this, z. Okay, now if I plot, you will see another trace here. Once it is run, see the trace here. Yeah, so it's little, we can focus on this red color line and identify the time period now where it is about to get 0. Okay, so it's 0 at around 4, near about 4. Okay, so you can see that what we wanted is we want a period of 4, so it should repeat 5 times within 20 seconds. We get it. So what is the format now? The main thing to understand here is the format. You should be able to generate all kind of desired waveform by your own. So format is y is equal to sine 2 pi f t, where t is time vector, f is input frequency. Okay, so I use this in order to get the desired waveform, and while explaining the moving average to you, let's quickly see that how this moving average helps, and getting how I can quickly control that shift. That is that would be easier here to understand. So let's just make one signal. I am just generating a random signal here. Okay, I'll switch to code in that case. So x, I'll name it as x is equal to, we'll copy this, so we'll say over time x is equal to, this is already the signal which we have. I am adding some more components to it, similar kind of components. 2 pi, let's make a frequency 1, so it repeats at 1 second, and I will also add a random noise here, random noise of size of x. Okay, and I need to delete this. Okay, You can even scale if you want to. If you want, you can put here C. C is nothing but your constant, which is getting multiplied by this random function. One important point is you can add your own controllability here. You can decide how much you want your C. So I'll quickly show that to you. We can add a slider here. Now many of you would have seen a slider in your while accessing a website or something. What you can do is you can set up the maximum minimum limit. You can also define a step how much you want to cause it, or so this is your C. Accordingly it will get multiplied by here your sign. What I'm trying to say with this, let's quickly visualize it. Let's quickly plot T and X. Okay, this is a separate plot, not with the existing plot. Okay, let's just quickly plot it. Yeah, unrecognized is the function or variable. Because here it is not defined, let me just give a variable as time. It's a small runtime issue, but can be easily resolved by adding this thing. So now you can see 3 different waveforms. Okay, what I can do is, if I just want to see our obtained graph, I just write here figure, and if I then run it, okay, I will get a separate graph like this. Okay, now what is the impact of this C? You can see here. You can see clearly by increasing this thing, this waveform is getting distorted accordingly. Basically we are adding more and more noise. It's the same thing what we obtained before, but added this noise. You can see that here clearly, right? This was our original without any kind of noise. It is looking like this, but if you add noise, little noise, okay. So how to remove this noise? I showed it to you that we can use moving average, right? So let's get the moving average. Again, you can define a moving average shift accordingly. Shift. We can put it as, again we'll put a slider. For time being, just give them a value from 0 to 20 with an increment of 1. Define a slider here. This will be used as a shift for moving average. Moving average version of X, let's define it. MA of X is equal to move min. This is the same function what we have used of X with shift. Okay, that is what we have defined. So now let's plot this on a separate graph as well. Agenda here is to show you how controllability can be achieved. Okay, so just a quick illustration. So now if I run this, okay, your C is defined, which is your constant. Again, yeah, the shift should be a finite number. That is what they are trying to say. But you can see that this was the original waveform. This was the original waveform. Okay, you can add, we have added little bit noise. That's 2.6 for now. Okay, it has altered your sinusoidal, some of sinusoidal waveform like this, and then by adding more and more shift in moving average, you will be able to get better and better result. In a way, you are kind of recovering your original signal from the noisy signal. So by just modifying these parameters, yeah, I believe you will get an idea. By reducing your scalar to the noise and increasing the shift, you are getting more and more closer to your original waveform. So I believe now this is clear. This is just to show you with this two scalar parameters. What we have seen last time with any three values, 11 point and 7 point and 3 point. But here, if you go further, you will get better and better signal. So your signal fidelity or signal quality will increase by having more and more shift in terms of moving average. Okay, so this is just a quick recap of what we have seen in the last lecture. Now let's see something called as Nyquist theorem. Very important when it comes to signal acquisition. Will not go in line by line what exactly the theorem says and all, but I just wanted to give you people a brief idea what it said. Suppose your band limited signal, you have a band limited signal. Now band limited signal means we have not covered the entire Fourier transform yet, but your signal will have a finite frequency component. Okay, so let's say your band limited signal has maximum frequency component. I'll just write component Fn. Okay, then it can be reconstructed by sampling at 2 into Fn frequency or more. What does it says is you have any signal which has a frequency Fm, then there is something called sampling. Now sampling means I should not say conversion, but it's a process to discretize or discretize the continuous signal. In simpler terms, to take values of continuous signal at equally space interval. Okay, so most of the modern day system use digitized, discretized signal processing. Your computer or your mobile, wherever you buy your computer or mobile, you will first ask what is the frequency supported or what is the crystal frequency, which is in terms of gigahertz, which means per second it supports x gigahertz operations. Okay, so in other words, what it says is whenever your continuous data you are taking per seconds, it operates or it partitions your continuous data into this many samples and process it. So that is basically funda of sampling. Okay, very important when it comes to signal processing and all, and even more important to acquire the value at a proper sample data rate. And why it is important and how it is related to your biomedical system. Again, whenever you are taking any kind of biomedical signal, it has its own frequency. Physiological signals, if you are recording your EEG, if you are recording your ECG, if you are recording any other signal, it has its own frequency. So generally, okay, sampling frequency is at least 10 times more than your maximum occurring frequency. Okay, we'll see why it is like this, but in order to just reconstruct is the word. If you want to get a better signal fidelity, if you want to get it with a proper quality, generally it can be 10 and even more than that. We'll quickly see that. So now all of you knows how to get sine wave for desired frequency. Let's just define it as f in, that's your input frequency. Instead of writing any value, I'll put a slider here which will give you a better idea of how frequency reads a frequency, so it cannot be negative here. I'll just increment it by 1 and let's just keep it limited to at 20, or 20 is fine for now. For the illustration, 20 is fine. Let's take sampling one more frequency, which is your sampling frequency. So Here again I'm repeating, input frequency is the frequency of your signal, sampling frequency is the frequency at which you are sampling that signal. Again we'll put a control slider and it's a frequency, but earlier we kept input frequency 0 to 20. So just to illustrate the other thing, we'll keep the maximum frequency as 200. Okay, you will get an idea how we are able to get better fidelity by sampling at higher frequency rate. Okay, so based on your sampling frequency you can get your duration, sample duration, nothing, just an inverse of your sampling frequency, right? Also you can get your output, will find out how much finite sequence you want. So let's take 200 sample, and now we need to get a time vector. So time vector can be obtained by 0 to ts. At every ts interval, sampling interval, it will record till how much time you need 200 samples. So n minus 1 into ts. Oops, yeah. And finally the signal. Okay, so it will be your sampled signal, sampled at fs frequency. I'll just name it as y sampled, right? Y sampled is equal to sine of 2 into pi into f input frequency into your time vector. Okay, and finally we would like to plot it as well, okay, with respect to time variable, right? This y sample. Yeah, I think that's fine. Also we will plot it in another variable, another figure. So I just added figure here, and let's draw it in some other color. Let's draw it in green color. Okay, so you'll get an idea. Now we need to set some input frequency, some sampling frequency. Okay, so let's just keep the input frequency as 5, and let's keep the sampled frequency, which should be at least greater than that. For now we'll keep it very high, just to give you people an idea. We'll keep it 100. Okay, so which is almost 20% more than maximum occurring frequency. Here the signal has only one frequency, that is 5. So maximum occurring frequency is 5, and this value we can put it as, one second, yeah, 99 is also fine. Okay, so you can see here your input frequency is 5, your sampling frequency is 99, which is almost 20% than that, and you are able to get a signal which is like input frequency 5. So we, and input frequency is 5, sampling is around 100. So in 200 sample you will get a data of 2 seconds. So that is what you are almost getting, a data of 2 seconds, which is your duration. And also you can see that in 1 second it is almost repeating 5 times. So it's able to reconstruct the 5 Hz signal using frequency of 99. You can change this to 100 as well by giving a manual value, typing it. Okay, so this is fine. We are okay with this. Now let's quickly decreasing the sampling frequency and observe the behavior. That is that will give you an idea how decreasing sampling frequency will affect the signal fidelity. This is a very simple signal, sinusoidal waveform with only one component. If you have more component, it will even affect more. So yeah, you can see here at 88 also you are able to see the proper sine wave. Let's further decrease it, make it 60, which is almost 12%, 12 times more than your input frequency. Okay, and let's see how it goes. So again, if you can see here, it is still processing, but yeah, if you can see here, you are able to see the sine wave. One important point to mention here is values also preserved, as well as the frequency of the input signal has not changed at all. You see it is starting at 0, 1 sec, 2, 3, 4, 5, 6, 5, around 5 it is stopped. So 5 means your input frequency is preserved. Okay, so for input frequency 5 hertz, 60 hertz is fine. Okay, let's go even beyond. So I told you around 10 is okay-ish to get your desired waveform with a higher fidelity. So now I have changed it to 50. So can you see little bit here? It is little tapered, or not proper, inconsistency. It is not exactly the sine wave which we want. So when you are sampling frequency, you can compare it. When you are sampling frequency, that's why I kept a slider here. It's very easy to analyze. When your sampling frequency is 100, what you are getting? You are getting a proper edges here, right? Proper sinusoidal. Yeah, just a second. Yeah, you can see the exact behavior of how sinusoidal input looks like, right? Whereas when I change this quickly to 50, you just focus on this shape. When I change this to 50, you can clearly see the tapered waveform, or non-ideal sinusoidal waveform. Now this is around 50 also, we are not able to get exactly the kind of waveform. What Nyquist theorem suggests is above 10 you can reconstruct, as in you can approximate, or you can vaguely get an idea about how your original signal look like. Okay, let's just make it 20 to make things, to keep the sampling rate reducing even further. So you can see that it's one more thing to notice here is when your sampling rate is 20 and your sample number of samples are 200. Okay, you are getting 10 seconds here, as you can see here. Additionally, your input frequency is 5. Okay, so but see this, the input frequency is maintained in 1 second only, 5 times it repeats, but you are getting almost a spike kind of waveform. Let's decrease it even further, but before that I'll just reduce the number of samples, so we will get to see the how many repetitions and all very clearly. We are now, as the sampling frequency is less than 20, around 10 or something, I think 50 samples should also fine. Okay, and let me just decrease the sampling frequency. We'll go to 10, which is exactly what Nyquist has suggested, like at least keep 10, but better the sampling frequency, the better the signal fidelity, but the computation power would be more. So if you see that here around 10, you're not getting the kind of waveform we should be getting, right? So greater than 10, if I go 11, then also you see almost like polarity is somehow maintained. Okay, but if you have to keep it greater than as I mentioned, greater than or equal to 10, or sampling frequency, let's keep it at least more than 2 into FM, which we have kept. So you see the kind of shape is preserved. Further, if you go down, what happens? You will not be able to reconstruct signal, you will not be able to get the waveform, you will be able to get the waveform, you will be able to plot it as well. Okay, but the shape of your original sine wave will not be preserved. This is not the kind of sine wave which we want to see. Further, if you go, it depends also on the exact value of sampling frequency and how it is related to your input frequency, etc. See, it is almost tapered. Your values are not also reaching up to the where it should reach, plus or minus 1 and all. So yeah, the moral of the story, idea here of this illustration is to give you people an idea. The higher the sampling frequency, let's keep it around 150. Okay, you will get a very nice waveform, but in this case you need to increase this number of samples to see a better visualization, to see the more repetitions, you'll get an idea. But you can clearly see this thing here, right? You are getting an excellent sine wave here because your sampling frequency is way higher. So yeah, concluding of what we have seen, that higher the sampling frequency, better the signal fidelity. Okay, mainly used in all biomedical potential acquisition. Okay, EEG, generally for EEG 250 Hz are fine because most of the components lies in most of the components lies in 50 hertz. uh, and then if you want even further components, you can increase the frequency. ECG heart rate, most of you knows, it will be around maximum around 100 hertz or 150 hertz, not more than that, right? That is what ECG's physiological range. That's why if you are making a device to record ECG, you can put it as a 1 kilohertz, a sampling frequency 1 kilohertz, or even 500 should be good enough to reconstruct your input ECG signal. Also, there is something called aliasing and all that also depends on the selection of your sampling frequency and input frequency. We'll not go into the detail in that, but that's also an important thing. And in the upcoming lectures, what we have seen is the frequencies. This is, as I mentioned, physiological range, right? Physiological range, 100 hertz for ECG, or 100 or 150. Range as in maximum frequency. Okay, there is some cardiac arrhythmia, some disorders which might force your heart pumping, or frequency of hearts even further. Here again, ECG, if I say physiological range, which means that it is around 100 hertz or let's say 50 hertz, which means it's a frequency range in normative condition. There are disorders like let's say epilepsy or something where it might go beyond that as well. Okay, but the moral of the story is, based on the physiological range, you should be able to at least approximate what should be the sampling frequency. Accordingly, you can able to reconstruct the original signal. So I believe you got some idea. Next time when we will meet, we'll see how to map your time domain waveform with frequency using Fourier transform, and how the computation complexity differs when you perform Fourier transform as per definition. Why FFT is called fast Fourier transform, we'll see in the next lecture. Bye, take care.